Hi everyone, my name is Azzolini. Thank you for coming to my talk today. I'm a second year PhD student at Arizona State University in the lab of Dr. Dale DiNardo. And this was my first project. I started it in the spring of my first year and have just recently collected all my data, and so everything that you're seeing is pretty new information. I'm going to be talking about the effect of reproduction on female oxidative state and the potential for vertical transfer to offspring in the absolutely ferocious children's pythons. So as a scientist, I'm broadly interested in conservation physiology, which strives to understand and predict how environmental stressors affect an organism's physiology, and then in turn, how those effects relate back into the environment and affect the population and ecosystem. Some environmental stressors that have been looked at are habitat loss, pollution, ocean acidification, just to name a few, and more recently, even less drastic stressors such as ecotourism. One approach to achieve these goals of conservation physiology is to establish reliable physiological bioindicators that can give information towards population health and estimate how well the population is doing. Measures such as stress hormone and immune function have already been well incorporated into conservation physiology, and an emerging physiological measure is that of oxidative stress. So here's a very simplified look at oxidative stress. Basically, all aerobic organisms are living in a constant dynamic balance between antioxidants and reactive oxygen species, or pro-oxidants. Antioxidants can be produced endogenously or ingested in the organism's diet, whereas reactive oxygen species are byproducts of metabolism. And they are not inherently dangerous, but when they outweigh or deplete antioxidant resources, that's when the organism is said to be in oxidative stress. In the short term, it can cause damage to biomolecules and inflammation, and in the long term, some studies have shown that it results in reduced survivorship and fecundity. So we're beginning to kind of incorporate oxidative stress into conservation physiology, and I found myself extremely interested in this topic because it's kind of new and emerging, and I started asking how might development, different life stages, different weather fluctuations, reproduction, temperature fluctuations, how do all of these things impact oxidative stress? And a lot of these questions have begun to be looked at in a variety of taxa, but as I was reviewing the literature, I noticed that there were a lot of inconsistencies, and it was really difficult to find any consistent trends that were very reliable throughout different taxa. So I strongly feel that before we can really understand the implications of oxidative stress as it relates to population health, we need to build more of a foundational knowledge base. And so the reason why I use snakes here is because at Arizona State, Dale has a captive colony of 84 children's pythons, which provide a really great opportunity for me to start testing some relationships, trying to untangle the mysteries a little bit more, and kind of just establish what are these baseline relationships between different life stages and oxidative state. So I started with what I thought would be relatively straightforward questions. What is the effect of reproduction on female oxidative state? As I had seen a couple of studies already answer this question in different taxa. But what I hadn't seen yet was whether maternal oxidative state can be vertically transferred to the offspring. So children's pythons were an excellent system to use for this question because they vary in the extent of energetic investment at different stages of reproduction, and they also have a lot of natural variation in both clutch size and quality. The stages that we were interested were first ovulation, which is the end of vitellogenesis. So these are capital breeders that will invest all of their resources into building up the follicles, and then once they ovulate, those follicles are ready to be fertilized. Luckily for us, they do a peri-ovulatory shed. So in addition to tracking follicle growth using ultrasonography, we also knew when they ovulated because they would shed. The next stage we were interested in was oviposition, so the day that the females lay their eggs, which would represent the end of energetic investment into reproduction. And here you can see just a little bit of the variation. This top clutch is not shelled as nicely as the bottom clutch. but the bottom clutch is a lot smaller than the top clutch. So, I mean, there's just all kinds of different clutches that come out. They all look a little bit different from each other. And then lastly, we wanted to just see a couple months down the road, what do they look like when they're just non-reproductive and living their normal snake lives. So here's a timeline of our experiment. The top part of the timeline is going to show the samples that we took from the offspring, and the bottom is showing the samples that we took from the mothers. All samples, whether they were plasma samples from the adults, yolk samples, or embryonic fluid samples, were analyzed using Diacron International's DROM and oxy-absorbent assay kits. DROMs measures reactive oxygen metabolites, which are basically just after biomolecules have come into contact with reactive oxygen species, they generate reactive oxygen metabolites. They're just a little bit more stable and easier to measure. The oxy-absorbent assay kits exposes the sample to a very strong oxidative attack and sees how well the sample is able to resist that oxidative attack. So this experimental design allows us to ask 3 different questions. How does oxidative state change throughout the reproductive cycle by comparing these 3 samples in green? Next, does maternal oxidative state influence that of the offspring by comparing oviposition samples to yolk samples that were taken the day that the females lay their clutch? So we would check them every single day. Once we saw that they laid their clutch, we would take 1 egg from each one to collect our yolk sample. Then we were able to compare how does oxidative state change throughout development by taking then 2 embryonic samples from each clutch. We tried to do a desiccation treatment. However, I'm not sure if that treatment worked or not, so unfortunately I'm not going to be able to speak to whether or not that influences oxidative state at all. But nonetheless, we still took a total of 3 samples from each female's clutch. So on to the results. This first graph here is looking at the change in DROMs throughout reproduction at ovulation, oviposition, and non-reproductive. We guessed that ovulation would have the highest level of DROMs because that's the most energetically costly phase to the mothers. And then oviposition would be a little bit lower, and non-reproductive would be the lowest. But surprisingly, we see probably not significant. Again, this data is very new, so I'm still working on all the statistics. Probably non-significant, but slightly higher levels of DROMs in non-reproductive animals. And our only potential explanation for this is that during breeding, children's pythons don't eat, but at this point, they're being fed weekly, and digestion can actually increase the metabolic rate of snakes, so that could be a reason, but again, I'm not sure whether this is even significant. And here is just showing that there's a lot of variation even within individuals. So it's really hard to kind of make any true trends from this data as of right now. And unfortunately, although we had full data sets for 25 females, we had a lot of difficulties with the assay kits. And so this is showing only 13 full female data sets. Next, moving on to antioxidants. So this is measuring antioxidant capacity. They seem to be relatively stable throughout all stages, but again, there is a lot of variation, and we were hoping that maybe the animals that were very high here within DROMs would also have very high antioxidants, but unfortunately we don't really see that. Next, does maternal oxidative state influence that of the offspring? So in the top, we're looking at DROMs, in the bottom, antioxidant capacity. On the x-axis, it's the yolk values, and on the y-axis is the yolk values, and on the x-axis is maternal values. And the green dots are representing ovulation, whereas the pink squares are representing the mother's values at oviposition. So again, unfortunately, we don't see any of the sort of relationships we were hoping to see here. And then moving on to measurements of clutch size. So on the x-axis, we're looking at maternal DROMs. Top graphs are showing ovulation, bottom at oviposition. And our measurements are total clutch mass in the first 2 graphs, viable clutch mass in the middle graphs, and then average egg mass in the third graphs. And while I want to see a negative relationship here, it really looks as though there's just a couple points driving that line that I'm hoping to see, and so really I think when you take those out, there's not much of a relationship here to be seen. But then when we look at antioxidants, so the same types of graph, total clutch mass, viable clutch mass, and average egg mass, x-axis is maternal antioxidant capacity. Particularly in ovulation, there does seem to be a negative correlation between the two. It's kind of there in opposition, but definitely not as strongly. And we were kind of surprised by this at first, but it could represent a potential trade-off where mothers that have larger clutches have to invest more antioxidants into their offspring, and so now their levels of antioxidant capacity have been lowered. But this is just a correlation. We weren't able to test for causation in this experiment. It's just one potential explanation we've come up with. And then, does oxidative state of the offspring change throughout embryonic development? Top box is showing the change in DROMs. The bottom box is showing the change in antioxidants. And so for DROMs, there doesn't appear to be any significant differences at any stage, whereas for antioxidants, the yolks have much higher antioxidant values, although I don't think that's really all that surprising. And this is, again, why I'm not sure whether or not my treatments work, because these, the control and treatments are pretty identical. So either it had no effect or our treatment didn't work, and unfortunately I'm not sure which is the case. So to summarize, we did not find evidence that reproduction influences maternal oxidative state. We saw that non-reproductive animals have very slightly higher DROMs. We found a negative correlation between maternal antioxidant values and measurements of clutch mass, but no correlation between maternal DROMs and measurements of clutch mass, nor were there a correlation between maternal oxidative state and yolk oxidative state. We saw that yolk antioxidant capacity is higher than embryonic antioxidant capacity, and that there was no significant difference between yolk DROMs and embryonic DROMs. So to bring this all back to my initial questions and fascination with oxidative state, I do still think it's a very important topic for conservation physiology, because we know that free radicals, reactive species, can cause damage to biomolecules, but I think that we need to proceed with caution, because there are still a lot of questions to be asked. My study probably raised more questions than it answered, and I think before we can really integrate oxidative stress physiology into conservation physiology, we need to have more of these just foundational studies looking at very basic effects, different life stages, and how that relates to oxidative state. So to summarize, life stage does not appear to influence oxidative state in Antares children. The negative correlation between maternal antioxidants and average egg mass could represent a trade-off, and yolks have higher antioxidant capacity than embryos. I'd like to thank my PI, Dr. Del Donardo, the Charlotte Magnum Student Support Program for helping me get here, Dr. Susanna French and Emily Virgin from Utah State University, all of my undergraduate helpers, but especially Anna Hernandez and Mary Thurston. Without all of these people, this work would not have been possible, and I would be happy to take any questions.
Do you know, or did you guys measure the actual metabolic rates of any of the females during this time?
No, we didn't. We kept them all uniformly at 31 degrees Celsius, though, throughout the entire experiment, to hopefully offset any differences in thermoregulation. But we didn't actually measure the metabolic rate.
Great talk, Jill. Ovulation in this species is the end of peak energetic investment. So how do you think your results might differ if you did it earlier throughout ovulation?
So actually,
or vitellogenesis?
Yeah, so work with rock iguanas has shown that early vitellogenesis, there is a positive relationship between DROMs and number of follicles, but that relationship does end at the end of vitellogenesis. So maybe we would see a different trend if we looked at early vitellogenesis, because that's absolutely right. That's when the actual investment is happening, whereas at the end of vitellogenesis, it's already been done. So I think that's something really important to think about. Thank you.